you give us a short introduction to your research?
So my research involves the interface of different materials. So when you combine two different materials together, the interface can have interesting and new properties that are not present in the bare materials when they are separated. An easy example is your laptop or your smartphone. Basically, things that needs processors. Processors are composed of billion of tiny devices called transistors, and this is essentially where you combine two different materials with what we call different electronic doping level, and then when they combine together, we can control their interface with gate voltage, whereby you can define your ones and zeros, and thus you can do something with the computational power with it. So that's the basic kind of zoom out view of my research, is to combine two different things together and see whether I can create a new interesting properties out of it.
How can the SCS instrument help you learn more about charge transfer dynamics across oxide interfaces?
Yes. So if you zoom in, the particular system that I'm interested in is what we call an interface between something called titanate. It is made from titanium, and nickelate. It is actually made from nickel. And then when you combine them together, something interesting happens. So titanate can have an excess electrons. Electrons are those that are running in the cables when you have electricity. And then these electrons can jump across the interface into the nickelate. And this jumped electron can change the properties of the nickelate layers. So it goes from metallic into insulating, and also from non-magnetic into magnetic. So the idea is, if we can trigger this electron transfer and therefore this changing of properties dynamically using light. So the idea is, if we can shoot a laser, an optical laser, into the titanate layer, this will create these excess electrons, and the electrons can jump over into the nickel in a very fast time scales, tiny fraction of a second, and then it will change this momentarily the properties of these nickelate layers. And we would like to see what is the changes using X-ray free electron lasers. So currently in the world, this can only be done in SCS instrument. This kind of setup can only be done here. And that's why I need this SCS really to do with, in this project, to do something with this project. Yes.
How can learning more about these dynamics help society in the future?
Yes, so let's go back to the computers and laptops and smartphone example before. So you know that if you go to an electronic store today and you want to buy a new laptop and you see the specifications, that you will notice that the processing, the speed of the processor is maybe something in the region of 2 to 3 gigahertz, or maybe 5 at maximum. And you know when was the first 1 gigahertz processors was being mass marketed? It was 20 years ago, more than 20 years ago, when I was still in middle school. So in the time frame of 20 years, we go from 1 to 5 gigahertz, which is not a lot actually. So I talk about that this electron transfer processes happens in a very fast time scales. We call this within, let's say, 1 picosecond. And then if you convert this into frequencies, which is basically just 1 over time, you get 1000 gigahertz. So if we can exploit these electron transfer processes into a new generation of devices, we can create a new type of processors that is essentially 200 times faster than what we got now. And then obviously in this current, nowadays we use computers in every aspect of our life. I mean, it is in our laptops, in our smartphones, in our TVs, sometimes even in our fridge, and we use them for work, for entertainment, also for medical purposes and so on. So we cannot escape from it, and then we have to be able to improve it. So that's my goal, that I can contribute to this invention of new and better and faster devices that can increase our quality of life.